Lesson 6. Big O, Big Omega, and Big Theta notation. When we speak of an algorithm's efficiency, we want to determine its scalability. That is, we want to know that when the algorithm is applied to a large data set, that it will finish relatively quickly. We can also talk about how much memory an algorithm requires, but for now we will focus on speed. We measure an algorithm's speed in terms of the growth in the number of operations relative to the input size. For the linear and binary search algorithms, for example, the input size is the number of elements that we are searching. Typically, we will use the letter n to represent an unknown input size, and we will talk about the growth in terms of n. To formalize our ideas of growth, there are three types of bounds that we will address here: Big O, Big Omega, and Big Theta. The definitions that we will use come from mathematics and are used to relate the growth in one function relative to another simpler one. Here we have the graphs of two real functions f of x and g of x, given by the gray and dashed arrows, which we use to indicate that the functions continue indefinitely. The function f of x is more complex, and we want to measure its growth in terms of the simpler function g of x. More specifically, we want to find a constant such that when we multiply it by the function g of x, it will bound the function f of x above from some point onward. Assuming that the graph of f of x does not intersect the graph of c times g of x after the point x0, we know that the graph of f of x remains in this white region for all x to the right of x0. In this case, we say that f of x is in big O of g of x. Formally, we say that f of x is in big O of g of x if there exist positive constants c and x0 such that f of x is less than or equal to c times g of x for all x greater than x0. On the other hand, we could bound the function f of x from below, like this. If such a constant exists such that c times g of x bounds f of x below from some point onward, then we say that f of x is in big omega of g of x. Formally, f of x is in big omega of g of x if there exist positive constants c and x0 such that f of x is greater than or equal to c times g of x for all x greater than or equal to x0. If there are constants such that g of x bounds the function f of x both from below and above, then we say that f of x is in big theta of g of x. Of course, the constants in this case are different, so we have labeled them c1 and c2 to clarify that. The x0 that we choose can be any value that is far enough out that f of x doesn't intersect either c1 times g of x or c2 times g of x anymore, and remains in this white area. Formally, we say that f of x is in big theta of g of x if there exist positive constants c1, c2, and x0 such that c1 times g of x is greater than or equal to f of x, which is greater than or equal to c2 times g of x for all x greater than or equal to x0. So far, we have shown what the situation looks like for general real functions. For algorithms, the input size is generally a positive integer, like the size of an array for a sorting algorithm. In this case, we can think of our f and g as functions on the positive integers. In mathematics, x is used to signify a real variable, while n is used to signify an integer variable. Like Hungarian notation in programming, this notation allows us to see more immediately what is going on, so we will use it. Using this notation, here we see the graphs of two example functions f of n and g of n, given by the solid gray and hollow black dots respectively. Notice that the graphs are made up of single dots instead of curves. This is because the functions are defined on integer values. Just as we had for the real functions, we can have constants such that when we multiply g of n by them, we bound f of n from some point onward, and the definitions are analogous. Here we have a constant multiple of g of n such that its graph is above the graph of f of n from some point onward. The last value that puts the graph below the graph of f of n is 2. So we can set n0 to 3, and we have f of n in the white areas below the graph of c times g of n from 3 onward. This is how we define big O of g of n. Formally, we say that f of n is in big O of g of n if there exists a positive real number c and a positive integer n0 such that f of n is less than or equal to c times g of n for all integers n greater than or equal to n0. Likewise, we might have a constant multiple of a function g of n such that c times g of n bounds f of n below from some point n0 onward. In this case, f of n is said to be in big omega of g of n. Formally, we say that f of n is in big omega of g of n if there exists a positive constant c and a positive integer n0 such that f of n is greater than or equal to c times g of n for all n greater than or equal to n0. Additionally, we can have two constant multiples of g of n that bound the function f of n on both sides from some point n0 onward. Here again, we say that f of n is in big theta of g of n. Formally, we say that f of n is in big theta of g of n if there exist positive constants c1 and c2 and a positive integer n0 such that c1 times g of n is greater than or equal to f of n, which is greater than or equal to c2 times g of n for all n greater than or equal to n0. Our purpose at this point is simply to give a visual impression of these bounds, along with an exact definition. In the coming lessons, we will give concrete examples of how they apply to specific algorithms so that these ideas become clearer. This concludes the lesson.